Hi everybody, this is Dr. Nigro with a Chem calculation screencast. This screencast is going to go over the three fundamental laws that we use in chemistry and some example calculations that utilize those laws. Just as a refresher, remember, theories explain why something happens and scientific laws explain how something happens. So those scientific laws tend to be accompanied by some sort of formula or mathematical calculation that you can do to support that particular law. All right, so the three fundamental laws were determined by early scientists in the 18 and 1700s. These laws came about mostly because the ability to experiment with a variety of compounds was improving. The understanding of what was going on in those reactions, such as products that were maybe gases and escaping, was better understood, and therefore all the products could be collected. So the scientists of that day and age just gained a better understanding of what was going on at the particulate level with these reactions, and then developed these scientific laws to explain the phenomenon that they were observing. All right, so the first law is one that you probably are familiar with. Conservation of mass, also sometimes known conservation of matter. It doesn't matter, you can state it either way. All right, but as the name of the law indicates, matter cannot be created or destroyed. All right, so what does that mean? It means that when you look at the amount of matter present in a reaction on the reactant side of that reaction, once the reaction occurs, all of that matter still has to be present on the product side. You can't make up any additional matter that can't join your reaction, and you cannot destroy any matter. So you have to conserve it. Whatever you have to start with has to be there at the end. All right, so if we think about it in terms of a simple reaction, let's just say A plus B forms the compound AB. And let's say I was running the reaction and I knew that I started with 5 grams of A and I made 15 grams of the product. Well, the law of conservation of matter lets me equate the two sides of my reaction. So I can put an equal sign in for the arrow, all right? And then the sum of the reactant side has to equal the sum or the value on the product side. So I put an X in for B. So 5 plus X has to equal 15. So that tells me that I must have started with 10 grams of that compound B. All right, so if you're ever working with a reaction and you know the masses of all components except for one, then that's where you can use conservation of mass to figure out what the missing value is. All right. From conservation of mass, we move on to the law of definite composition. And I've actually heard this called many things: definite composition, constant composition. They all mean the same thing. I tend to go with definite composition. And basically, all right, once you ID a chemical compound by formula, then all instances of that compound must have the same amount of each element by mass. All right, that's a lot of words. What does that really mean? It means that once you define something, let's use water for an example. Once you define something, or that compound that you've isolated is H2O, you've done your analysis. That means that any other time someone else finds a compound and they identify it as H2O, the two compounds must have the same percentage of oxygen and hydrogen, no matter what the source is of that compound or the state of matter. So in other words, the amount of elements present in that compound must be the same for it to be considered water. If you find a second compound and it does not have the same percentages, then you have a different compound. It's not water. All right, so if we think about it in terms of H2O, H2O is 11.2% hydrogen by mass and 88.8% oxygen. So as long as I find another compound with that exact same percentage profile, then I can identify that as water. If I have a second compound, let's call it X, and I find that it has 5.2% hydrogen and 94.8% oxygen, these are not the same compound. Compound X must be something different. So when scientists identify new compounds, one thing that they can do is determine the percentage by mass of each element within that compound and use that to compare it to known compound profiles. And that either can put them in the ballpark of what it might be or eliminate compounds that it definitely cannot be. All right, so the law of definite composition is pretty handy to the scientists. All right, the last law is the law of multiple proportions. All right, and the law of multiple proportions, in my opinion, is the most complicated mathematically. It's not difficult in terms of understanding. All right, so basically, when two or more elements can combine to form a series of compounds, they must do so in whole number ratios. This makes a lot of sense. You can't have half atoms. They have to be whole atoms. So if you want to form a compound, it has to be whole atoms of the elements. You can have more than one atom of an element within a particular compound, but what you can't have is partial atoms. And that's what the law of multiple proportions is basically telling us. If we're going to have a series of combinations between two or more elements, they must always combine in whole number ratios. So for example, nitrogen and oxygen can form a whole bunch. They can form nitrogen monoxide. They can form nitrogen dioxide, and they can form dinitrogen monoxide. But the key here is that they are all in whole number ratios. All right, so when you're trying to figure out what that formula is, my advice is you use the mass of, we'll just use nitrogen as an example, of nitrogen in the compound and the mass of oxygen in that compound. So this is in your compound, and you set that equal to one of them, and then the other is unknown. All right, and so the mass of one atom, so the well, we're going to use the mass of a mole, but we'll say one atom of nitrogen has a mass of 14.01 atomic mass units. All right, and then I want to see, well, then how many atomic mass units of my other element are present. All right, if it turns out to be 16, which is the atomic mass of oxygen, then I know that for every one nitrogen, there's one oxygen. If it turns out to be 32, then I know that for every one nitrogen, there are two oxygens. If it turns out to be 8, then I know that I have doubled the amount of nitrogen versus oxygen. All right, I'm going to show you how to use this law in the problems below. So don't worry if this mathematical part doesn't make sense yet. It will once you see it in action. All right, so these are our 3 fundamental laws. So let's work our problem. All right, so our lab group conducts several experiments where we separate the elements within 2 samples, A and B, and collect the below experimental data. All right, so we have sample A, we've got the mass of the sample and the mass of the oxygen within that sample. And then for sample B, we have the mass of the sample and then the mass of sulfur within that sample. So we're dealing with compounds that contain sulfur and oxygen. All right, are the 2 samples of the compound the same or different? All right, support your conclusions with a calculation. All right, so I'm going to use the law of definite composition here. Oops. All right. I'm going to determine the percent by mass of each element within each compound, and I'm going to compare them. If the two samples have the same mass percentages, then I know they're the same compound. If they don't, then I know they're different. All right, so let's start with compound A. All right, I know the mass of oxygen, so I can find the percent of oxygen. Remember, a percentage is just part divided by whole. So in this case, the amount of your element, 37.46 grams, divided by the mass of the whole sample, which is 75 grams. And then you multiply that by 100%, and we're going to get a percentage here of 49.95% oxygen. All right, so now I want to figure out the percentage of sulfur. So this is where the law of conservation of matter comes in. All right, I know that the whole sample has a mass of 75, and I know the mass of oxygen. The rest of the mass, the difference between those two, has to be the amount of sulfur. All right, so I could say 75.00 grams of total minus the 37.46 grams of oxygen, and that's going to give us the amount of sulfur that is present. So 37.46, oops, 75 minus 37.46. And we get a value of 37.54 grams of sulfur. Okay, and so then to determine the percentage of sulfur, we do the same thing, except this time we say 37.54 grams of sulfur divided by 75 grams total times 100%. And that's going to have a percentage of 50.05%. And that's the sulfur. All right, so that's compound A. Now we look at compound B. All right, so this time we know the amount of sulfur. So we're going to find the percentage of sulfur. All right, and that's going to be equal to the part, which is 50.06 grams of sulfur, divided by our whole. And here the sample's mass is 125 grams times 100%. All right, we do our calculation and we find that this compound contains 40.05% sulfur. All right, so I look at this amount and then the amount in compound A, and those two are not the same. Now, I can go ahead and do the percentage of oxygen if I like, but it's not really necessary because once I determine that one of the elements is not the same by mass, then the compounds cannot be the same. So I can stop right here, all right? But let's say I wanted to determine the percentage of oxygen. In this case, I could either use the law of conservation of mass and subtract the 50.06 from 125, or because I know there are only two elements here, I can just subtract the percentage, 40.05 from 100, and the difference is going to be the percentage of oxygen. Either way is going to work. And can you see here as well that that percentage of oxygen does not match the percentage of oxygen in compound A. So not the same. All right, so now let's move down to part B. All right, so part B says, well, then what is the formula? All right, so this time we want to find the formula of the compound in each sample. So this is a series of compounds that contain sulfur and oxygen. We know they have to combine in whole number ratios, so I'll be using the law of multiple proportions to determine what these formulas are. All right, remember, for this law, you need to compare the elements to each other. All right, so we're not going to be comparing an element to the total or an element to the sample like we did with the law of definite composition. We're going to be comparing the elements to each other. All right, now you can do this a couple different ways. I'm going to show you the way I like to do it. All right, because in part A, I determine the percentages of each element within the compound, I can use those. I can say 49.95% oxygen divided by 50.05% sulfur. And I'm going to set that in ratio to the mass of one atom of sulfur and figure out, well, then what is the mass of oxygen present within that sample? All right, so I'm going to put my unknown up top since I put my oxygen percentage up top. and 1 atom of sulfur has an atomic mass of 32.07 AMUs. All right, and I got that value off of the periodic table. So make sure you have your periodic table handle. All right, so I'm going to cross multiply, and I'm going to find that the amount of, or the mass of the oxygen present is equal to 32.01 atomic mass units. All right, so I go look at the periodic table and I ask myself, well, how much does 1 atom? All right, so 1 atom has an atomic mass of 16, which means that I must have 2 atoms of oxygen here. All right, so remember, each atom of oxygen has a mass of 16 AMUs. So if I have 32 AMUs of oxygen, I must have, sorry about that, let me move this up, 2 atoms of oxygen. So my formula here must be SO2. All right, now let's look at B. All right, so I'm going to do B a little bit differently. All right, instead of using the percentages, I'm going to use the mass values. All right, so I know that I have 50.06 grams of sulfur in this sample, and if I use the law of conservation of mass, I can subtract that amount from the 125, and that will tell me the mass of oxygen, which turns out to be 74.94 grams of oxygen. All right, and then again, I'm going to set it equal in ratio to the mass of a single atom of sulfur, so 32.07 AMUs of sulfur over an unknown mass of oxygen. I'm going to cross multiply, and this time I find that I have 48.00 AMU of oxygen. All right, so I ask myself, well, then how many atoms of oxygen must be present? So I divide that by the mass of 1 atom, 16 AMUs, and I find that I must have, let's do math today, 3 atoms of oxygen. So this must be SO3. All right, so that's how we can determine the formula of these elements, okay? Not elements, sorry, formula of these compounds. All right, let's look at our last problem. Your teacher finds a third unlabeled bottle, sample C, and asks for our analysis again. So first, determine whether the sample matches A or B, and if it's different, determine its formula. All right, so remember, to determine if sample C is the same or different, I'm going to do the percentage of sulfur and oxygen within that sample. So if I start with sulfur, I have 10.34 grams of sulfur per 15.50 grams of sample times 100%. And I find that I have 66.73% sulfur present. All right, now to check oxygen, I can just say 100% minus that 66.73% sulfur is going to give me that oxygen, which turns out to be 32.27% oxygen. So I look at these two values and I compare to what I saw with A and B, and they are not the same. All right, I have different mass percentages of sulfur and oxygen, so the compounds cannot be the same. All right, so now, since we know it's different, let's figure out what it is. Now, I've been doing sulfur, comparing the amount of oxygen to sulfur. This time I'm going to do it the other way. All right, so I'm going to say, all right, I've got 5.157 grams of oxygen, and I have 10.34 grams of sulfur. All right, I know that 1 atom of oxygen has a mass of 16 AMUs, so then what mass of sulfur must be present within my sample? All right, so I do my math, and I find that I have 32.08 AMU oops, of sulfur. Now, I want to divide that by the mass of one sulfur atom, which is 32.07. So I'm going to get a 1 here, which tells me that for every one oxygen, I have one sulfur. So my formula here must just be SO. All right. If I did it the other way, all right, so 5.157 grams of oxygen divided by 10.34 grams of sulfur, and I set the oxygen to 0 and put in 32.07 AMUs for that one atom of sulfur, I'm going to find that the mass of oxygen present is 15.99 AMUs. And if I divide that by the mass of one atom, which is 16, you can see we're going to get a 1 here. All right, so that also tells us the formula is SO. All right, so it doesn't matter which one you choose to be one atom rather. All right, you just need to be consistent when you set up your ratio. It also doesn't matter if you use the mass percentage values or the actual mass values given. You just need to be consistent with how you set up your ratio. Okay, so those are the calculations that accompany these 3 fundamental laws of chemistry. Make sure that you understand what the laws are and then how you can use them mathematically, what you can use them to determine about your samples.